In Chapter 10, we're going to continue on with our hypothesis testing. This time we'll be dealing with 2 samples instead of 1 sample. I will throw in a few things dealing with confidence intervals with 2 samples as well, so we'll look at those. Most of what we're going to be doing is going to be on the calculator. The formulas, I will give you a few of them. Not all of them are pretty complicated, so the calculator does a very nice job with these. The first thing that we need to do when we're dealing with 2 samples is to figure out whether we have independent groups or whether we have matched pairs. Because if we have independent groups, we're going to use the 2 sample tests. If we have matched pairs, we're actually going to use a 1 sample test and use the differences. So in the independent group, we're going to make sure on our calculator we use our 2 sample tests. And for the matched pairs, we'll use our 1 sample. Okay. The difference between the two is in an independent group, you're going to actually have 2 separate populations. So, for example, you may have male versus female. You may be doing a test to decide if there's a difference between the male and the female. Or it could be somebody taking the medicine versus placebo. Where in the matched pair, you're dealing with something like a pre-post situation. You have the same subjects looking at scores prior to some sort of treatment and then post some sort of treatment. Sometimes we look at that as before, after. But we're looking at the difference when we talk about a 1 sample test. So we won't actually have 2 separate numbers that we put into our calculator. We'll just find the difference for each individual subject. There's only 1 population to look at. So here are some examples so we can decide by reading some application problems, would this be an independent group situation or would it be a matched pair? So let's look at the 21.1, how sweet it is. It says choose 10 agricultural plots of land located in different regions of the state. Plant half of each plot with 1 variety of sweet corn and the other with a different variety. Compare the sugar contents of both varieties of corn. Would we consider that to be independent groups or a matched pair? So if you think about this, you have 10 plots and you're splitting them in half. So one half you'll have 1 treatment and the other half you'll have the other treatment. You probably want to compare for that 1 individual plot the 2 separate treatments. So this would be considered a matched pair. Okay, it's not a pre, post, before, after, but it is just one population. We're looking at 1 population of the agricultural plots. We're looking at a sample of size 10, and for each plot, we're getting 2 different pieces of information. Okay, so in the next example, we have 21.2, exercise and memory. To examine the effect of physical exertion on the memory of a witnessed event, researchers randomly divided police officers into 2 groups. One group completed a high-intensity physical assault exercise, and the other did no exercise. Both groups were then placed in a live, occupationally relevant scenario. After the scenario, the mean scores on an exam testing recall of what was witnessed during the scenario were compared. So in this case, you can see that I have 2 independent groups here. The ones that had the high-intensity physical assault exercise and the other ones that did not have that. So I should put 2 independent samples. Okay. In 21.3, the smartphone battery life. To check the lifetime of a new battery in a soon-to-be-released smartphone, an engineer surfed the web over 4G continuously, beginning with a fully charged battery, until the battery was drained. The engineer repeated this for a total of 10 times. He compared the results with the lifetime of 12.8 hours for the current battery used in the company's smartphone. So this is different than the last 2 examples. I'm looking at 1 sample and I'm comparing it to something that we had already of the current battery, the 12.8 hours. So if you recall, this is what we've been doing in Chapter 9. This is actually just a 1 sample test, similar to what we already have been working on. So in the last example, it says smartphone battery life continued. So another engineer is checking the lifetime of the new battery with a prototype that she just developed. She wants to know how the lifetimes of the new battery and her prototype compare. She measures the lifetime of the new battery and her prototype by continuously surfing the web over 4G until the battery is drained. She repeats this a total of 10 times for each type of battery. So in this case, you're doing the same thing but for two separate types of batteries. So would this be a one sample, a two independent samples, or a matched pair? So hopefully you set it to independent samples because you are comparing two separate batteries and you're looking at the lifetime of the two separate batteries. It's not one battery that we're doing a pre and a post or a before and an after, and it's definitely not just one sample. We're looking at two separate things. Okay, so now that we know what we're exactly looking at as far as the two independent samples, let's look at our conditions and the formulas that we would need to use to do a hypothesis test with two samples. So our conditions, we've talked about conditions a lot. We need the two simple random samples from two distinct populations. So we're looking at men and women, or we're looking at one group that took one test or had some sort of treatment done to them and another group that did not. Okay, the samples are independent. We need to have a normal distribution for both populations. We want to make sure that they're at least similar in shape with no strong outliers. And remember, it's always good to have large samples. So that's going to help. Okay. In this case, my mu and my sigma are unknown for both populations. In the next lesson, we'll go over when the sigma is known, which is not very practical. But most of the time, we do not know our population mean nor our population standard deviation, and so we're going to have to use this test. If you remember, when we don't know our sigma, what test statistic do we generally deal with? Our t. So we are going to be looking at t in this particular case as well. Okay. Our variables, and this is where I think some people are getting a little confused as we did the one sample. It gets a little bit more confusing now that we have two. But our variables, remember, for our population are our Greek letters, mu and sigma. And for our sample, we use x bar, s, and n. Now that we have two samples from two different populations, we just need to use subscripts for the 1 and the 2 so we don't get them confused. So just make sure you're consistent. Population 1 is always going to have the subscript 1, and population 2 is going to have the subscript 2. So for our formulas, you'll see that they're a little tedious. Our standard error of difference in sample means is, remember, going to be basically our standard deviation of the sampling distribution. And in this case, it's going to be of the difference between the two sample means. Okay, our confidence interval is going to look very similar to our typical confidence interval formula. Remember, because we do not know sigma, we're using a t instead of a z. So we're going to have to figure out what that t is based on degrees of freedom. Now, degrees of freedoms are a little more complicated because I'm dealing with two samples. So I can't just take n minus 1 like we did before. What we have to do is either, if we're using a calculator, it will give me a degrees of freedom that may not be an integer, but it has a pretty complicated formula to figure it out. Or I can use option 2, and I forgot to write my subscripts here, where you take n1, the first sample, minus 1, and the second sample minus 1, and you take the smaller of the two. Okay, remember what happens when I have a smaller degrees of freedom and I'm looking up my t's in my table. My t's are going to actually be larger, so that would be a more conservative option to go with that option 2. We're in general going to use our calculator because these formulas are pretty complicated, and our calculator does a very nice job of coming up with confidence intervals and our test statistic. Okay, for our test of hypothesis or our hypothesis test, remember that we need a null and alternative hypotheses. So our null in this case, since we are dealing with two populations, is going to be that the actual population means are equal. So mu1 equals mu2. The other option is to actually take the difference between the two and say that the difference is 0. Personally, I like the first option, and that's what the calculator is going to give it to you as. So you're going to have the mu1 equals the mu2. Okay. The alternative hypothesis is either going to be less than, greater than, or not equal to. But in this case, you do need to be careful. So just make sure that if you use the less than, you always, your population 1 is going to be the one that you want to be less than the population 2. Now, you'll see when I do some examples that you can change those. If you always want to use less than, you can always make sure your population 1 is the one that you want to be less than the population 2. It's up to you, or you can switch it to greater than. And the not equal, remember, is when they don't say less than or greater than. Remember, for all of our test of hypothesis, we need a test statistic. So in this case, since our sigmas are unknown, we're going to have a test statistic of t, and we're going to use this formula right here. Once again, our calculator is going to give us our test statistic, but you will notice that I'm using S and not sigma in these problems because I don't know what sigma is. Okay. To find the p-value, we use the same method that we would in a one-sample t-test. Remember, our p-value, I'm going to start with a difference of 0, and let's say I get a test statistic of somewhere right here, and it's a one-tailed. So I have that alternative, then my p-value is going to be the area of that shaded region right there. Okay, what does the p-value mean? It means that it's the probability that you would get a test statistic as far away from 0 or further if there is actually no difference in those population means, meaning the difference is actually 0.